It is chapter 22. We are going to talk about magnetism. I wish that you will be able to watch the videos that I have posted already. And just in general, we are going to talk about magnets, magnetic forces, and some of the very important applications related to magnetism. Okay, the first thing I want to talk about is magnets. And here we are talking about that there are like natural magnets as was like outlined in the video, and of course now we are making these magnets in I will say like we make artificial. Now, magnets, they have two poles. And we know that one of them, we are going to call it north magnetic pole and south magnetic pole. Yeah, sometimes we call this like north seeking and south seeking. Sorry. These really areas or like points in the magnet where we are going to have the magnetism very strong. A universal characteristic of all magnets that like poles repel and unlike attract, very similar to electric charges. Also, we hear what is really different from statics or like electricity, that we cannot separate the north and south poles. Okay, if we are going to cut a magnet, okay, let me get this picture. This picture, maybe it is more its place, it should be like up. Share, then I'm gonna say copy. I'm gonna put it here because here I can say it should be here because like here I'm showing you that when we cut that magnet into two pieces, again the magnet is gonna have a south and a north, and then when we cut it again and again, then we cannot isolate south and north poles. Always, even if you're gonna have a tiny thing, you're going to get these poles. Also, I want to share with you here the I will say the simulation that we have, where we are talking about magnets. Okay, I lost it. It seems where did I get it initially? It's oh, where did it go? It should be okay. Magnets. Yeah, ferromagnetism. This is the one. Okay, now here, of course, here we are going to show the field, and I will talk about this. Do you remember when we did the magnetic field lines? These are really very similar. We have what is called magnetic forces, magnetic field lines. Here we have the south and the north pole, And you can see that the north of the compass is pulled by the, the south of the. Okay, also here I want to show you okay, let me see here why it's. Okay, I want to show you the meter. There is a meter showing you that here, look here, it's like B, it is the strength of the magnetic field. It's very strong here. Also, it's very strong here. But here, look here, it's very small. And also remember, when we were talking about the electric field lines, we said the density is going to tell you where it is really very strong. Like you can see here that the line are really very dense. And something that you need to know that also, that the magnetic field lines, they're going to come out of the north and enter into the south. And also, we can say that inside it's gonna be the opposite. And this is like showing you so many, like this is like inside, look here. Okay. Outside it is from north to south, and inside it is from south to north, so that the magnetic field lines are really closed lines. Now, also something that we need to know that inside the earth, because of the molten metals that we have and their motion, and we're gonna know later that whenever we have a moving electric charge is gonna create a magnetic field. Then we have inside the earth, we have a big magnet, where its south pole is gonna be hitting the north geographic pole, as the picture is showing you here. Okay, and the north pole of that magnet is hitting the south geographic pole. Now, when you have your magnet free in the room, suspended with a string, you will find that the north, of course, this is the north, is going to be attracted to the south magnetic pole, which means it's gonna show you the north geographic pole. And this is the reason why we call it north seeking pole. And like that one south is going to be attracted to the north, and this is the reason why we are calling it south seeking pole. Like if you have bunch of I will say magnets, all of them, they're gonna be oriented in the same direction. All right, now let's move to the next, and we are going to classify materials. Okay, let me get rid of these here. We're going to classify materials into different categories, but I am very interested in one type of material, which we call them ferromagnetic materials. Ferromagnetic materials. These are examples of these are iron, cobalt, nickel, and there are many also artificial things, or like we have made, like I will say, materials that we can make in the lab. Their name is ferromagnetic. It is from the Latin word for iron, which is ferrum. Now, one thing that is really very important about these materials, that we can make them strong and permanent. Magnets. Now, I will say other materials, maybe they will not be able to be magnetized easily. And actually, I will say these materials, usually the one that I'm talking about, the ferromagnetic, we are really dealing with them here and using them for magnets. Here I have an unmagnetized piece of iron is placed like in here between the two magnets, okay, and it is heated and then cooled or simply tapped. When cold, the iron becomes permanent magnet with the poles aligned as shown here, the north and the south in this here. Okay, its south pole is adjacent to the north pole of the original magnet, and its north pole is adjacent to the south. Actually, this is how we magnetize materials. Now, something that we need to know that there is what's the reason for these materials that they can be magnetized or they can easily be made magnets. We have regions within the material, we call them domains. And these domains, as if they are really small bar magnets. Now, bar magnets are really these, something like this. Okay, then these like are the domains. They are really as if they are really small domains existing in the material. And I will say if the material here is unmagnetized, then the domains are really randomly oriented in all directions. When magnetized by an external field, the domains will start being aligned, as you can see here. And I will say we are going to find that even like the small atoms, they're going to act as tiny bar magnets, and they are going to be having like that direction for magnetism and making that material is like we can make it like permanent magnets if the material is heated and then cooled or simply tapped in the presence of other magnets. Also, we can do the opposite. We can demagnetize, means removing the magnetism, by hard blows or by heating in the absence of another magnet. Okay, there are other types of like magnets that we are really interested in, and they're very important in our applications. We call them electromagnets, and that is really something that is whenever we have electricity, this material is going to be a magnet, and then removing is going to be we don't know more. It's not really a magnet. These, we call them temporarily induced magnets. And they are really very important in many like applications. For example, they can be used to remove junk, or I will say wrecking yard. Anything to remove the wrecking yard, let's say junk or materials. And drop it somewhere else. Okay, something really important is magnetic field and magnetic field lines. Okay, remember, magnetism is, or magnetic force, it's one type of field forces, and there is a region around the magnet where the magnetism is strong, and we need to to find what is really the direction. Now, one more thing that maybe here we need to know is I can use a compass to find the direction. To, let's say, to map first. To map the magnetic field lines like I did in the FIT, which is the simulation. Okay, then there we can see that the magnets, we can use actually I would say the compass to show us the direction. Now, we can say also here that electric current, where the a region around the magnet where the magnetic force is acting. Okay, I want to add here that also electric currents are really the source of all magnetism. And here showing you that I can use a small compass, like for this here, the number A here, I have a circular current loop, and the current direction is in this direction. Now, what I can do is I can use what is called the right-hand rule, where I will be able to use my fingers to show the direction of the current, and then my thumb is gonna show magnetic field direction. Also, this is a straight wire. Again, it's the opposite. I can use my thumb to show the direction, my right hand rule, right hand rule. Okay, right hand rule, I can show here that I is upward, which is my thumb, and then the rest of my fingers, they're gonna point in the direction of B, which is the magnetic field. Look here, this is my thumb is showing up, and then my hand is going to show the direction of the magnetic field. I can use the cross to show that B is going to be in, and the dot to say that the magnetic field here is out. Okay, and we are going to use that notation all through because we are going to deal with magnetic fields more later. Some of the notes here that the direction of the magnetic field always it is tangent to the line at any point in space. For example, if I said like I will talk about that wire here, okay, and then I said it's gonna be like a circle. I said like this here for the magnetic field, and then I'm asking you what is the direction of the magnetic field here. Then you're gonna draw that tangent to show what is really the direction. And in this case here, we said is gonna be into the page, and that is gonna be out of the page because it will enter the page and leave from the other side. Also, the strength of the field is proportional to the closeness of the lines. This is the density of lines, very similar with what we did with electricity. It is exactly proportional to the number of lines per unit perpendicular to the lines, and we call this areal density. Magnetic field lines, they cannot cross each other. Okay, then the magnitude of the field at any point is unique. Magnetic field lines are continuous, okay, then forming closed loops without beginning or ending. As we said, they're gonna go from North Pole to the South Pole outside the magnet and from south to north inside the magnet. Okay, now I will move to the next thing, which is I'm gonna start talking about magnetic forces on okay, let me add a page here. I will start, this is 22.4. I'm gonna talk about magnetic field strength and talking about force on a moving charge in a magnetic field. And here there is something that we are really to know that anytime we have a field, then I will say a magnetic field will create a force. Then I will say magnetic fields exert forces on moving charges. Then if you have a charge that is not in motion, we don't have a force on it. Now the magnitude of the force, okay, this is the magnitude, can be calculated as the charge Q times V times B times sine theta. Now Q, it is the charge in coulombs. V, it is the velocity in meters per second. And B, it is the strength of magnetic field, and it is measured in Tesla. Now, okay, let me start first with Tesla. Of course, sine theta doesn't have, it doesn't have an angle, but it doesn't have a unit, I mean. This is really theta. It's the angle between the directions of V and B vectors. All right, I want to use this equation to calculate what is really the value of Tesla. Then I'm gonna use it without having the sign. I will say B is F over QV, and that is 1 Newton Coulomb meters per second for speed or for velocity. This is gonna be 1 Newton over, we know that Coulomb per second is gonna be ampere times meters. Then this is really derivation of what is really 1 Tesla T. Okay, then this is really important. That Tesla, it's a little bit large, and therefore we can use a smaller unit. And this is like the old unit. We call it Gauss. And 1G, it is 10 to minus 4 Tesla. Okay, now one more important thing is I will say that the direction now, because we discussed the magnitude, then now I will talk about the direction of the magnetic force. This is very important. Okay, that force, it is always perpendicular to the plane formed by V and B. What does that mean? If I have, let's say this is my B along the x-axis and my, let's say V along the y-axis, then this is the direction of the force along the z-axis. Okay, just look at the corner of the room, and that is really, we can determine it using the right hand rule. Okay, one, because we might have like more than one. This is RHR1, and I want to show you here what is really the rule. Okay, then I'm gonna move to the textbook where I want to show you the diagram that is gonna show us the rule. No, not this one, the one before. This is the one. Okay, now you can see here, this is RH1. Okay, let me get it, and it's much better if I'm gonna have it also with the rest of the lecture. I think I took a picture of that, but maybe it's somewhere else. But let me, okay, have it here. Okay, then you can see that here, let's say, assume that my thumb, I have V, and then the direction of my fingers is B, then the force is gonna be perpendicular to my hand. Okay, and this is really how we can find the magnitude of the the direction of the direction of the force. Okay, now before this also I want to do this exercise with you just to show you how we are going to work on these problems. Okay, then. Okay, here, what is the direction of the magnetic force on a positive charge that moves as shown in each of the 6 cases shown in the figure? I want you to practice this, and here, if I will have my thumb pointing down for V, and then my fingers, they're gonna be pointing. Of course, remember you have to use your right hand, and then your magnetic field, it is leaving, out of the page here. Then F, it should be perpendicular on these 2 vectors, and it should be to the right. For like this one here, let me maybe draw something here. Okay, I have, I'm gonna say in terms of the Z and the Y and the X-axis, it's gonna be much easier for you. Now here, B, it's along plus Z, and V, this is B magnetic field, and V, it is along, I'm gonna just show you one of these. V, it is plus Y. Then I have, this is V, and that is Z. Okay, and of course here you can see like the Z, it is towards you and this is down, and then you're gonna find that the force should be in this direction so that it will be perpendicular on the plane for both. Okay, for this one, the second one, okay, try always to practice this. We have V up, V, it is, this is for A. For B, let me repeat that. This is along the Y axis, and that one is along this along the Z, the X axis, the B. Then I will find that perpendicular in these is going to be into the page. Just here, I want you to, I have completed the forces. Okay, this one is going to be upward, this one to the right, this one downward. Check these, and then you might ask me later if you did not get these. For this one here, for number D, I will find that if I will do the magnitude, is going to be sine 180, and sine 180 is 0, and therefore the force is 0. Now, all these directions are for positive charges. If I want to get, for a negative charge, I will say, after I will find the direction, I will say the force should be in the opposite direction. One of the most important, before I solve this problem, it is one of the most important, I will say, applications related to, this topic. It is when I have, a charge that is gonna come initially with a velocity that is perpendicular to the magnetic field. My B here is going to be N, and I will say here the velocity is going to be perpendicular, and therefore the force here is going to create a centripetal force. And that Fc, remember this is from from physics, 120, chapter 6. That force, the magnetic, is going to create this type, and therefore I can find the radius for that motion as mv divided by qb. And this is one of the actually the most important applications where we have accelerators, where we're going to accelerate a nuclear material. Okay, here a cosmic ray electron moves at this speed 7.5 10 to the 6 meters per second, perpendicular to the Earth magnetic field at an altitude where the field strength is 1 10 to minus 5 Tesla. What is the radius of the circular path of the electron is going to follow? It's the same exact thing. R is going to be mv divided by qb. I have, this is the mass of the electron. This is the charge of the electron, and that is its velocity, and this one is the strength of the magnetic field, and I was able to calculate that as 4.27 meters. I'm gonna stop here and then move to the next in another video. Thank you.